Well, that's a philosophical issue.
Okay, I'll try to cover this. Yeah.
Okay, well, let's get started. Well, it's my pleasure today to have Hao Geng visiting us. Hao got his PhD in Washington, Seattle.
Yeah.
And then after that, he went straight to Harvard.
Yeah.
Straight to Harvard as his first postdoc, and that's where he is today. And he's going to tell us about this very interesting work about the mechanism behind the information encoding behind.
Okay, thank you very much for the invitation, and also thanks everyone for attending this talk. I'm very happy to be here. So like Tony said, today I'll talk about this paper. Like I'll mostly talk about this paper uploaded almost a year ago. So the title is the mechanism behind the information encoding for Entanglement Island. Since I'm talking about this thing called Entanglement Island, let me first give you the definition of Entanglement Island. So the definition, Entanglement Island, Entanglement Islands are subregions in the gravitational universe, and whose information is.
Sorry, I have a non-physics request. Is it possible to zoom in? Because I'm getting old and this is too small.
Zoom in.
Because yeah, that's the most microscopic text I've ever seen in a seminar.
Zoom into the word or zoom.
Yeah, like is it going to be all this size text?
Okay.
Because that's a problem for many of us.
Later.
Yeah. No, this is it possible to zoom in? Because this is going to be difficult.
The only thing.
I mean, like.
The only thing we can do is that.
Oh, I see. We're sharing.
So do you literally have pages?
Yeah.
Yeah, I do have
Slide.
So we can either.
That's an interesting approach. Okay,
But
fine.
this is large.
Maybe but it's hard to.
No, it's okay. It's okay. I mean, it's fine. If this is how the speaker wants it, it's fine. Whatever.
No, you can expand it. So
It's okay. Don't worry about it. Maybe I'm the only one. It's okay.
I have bad eyes.
It's okay. I got it.
I hear you. Yeah. It is a bit weird. So it is only a sub-region of this.
you take only half of the screen area, but if you increase it to full screen, it will be.
This is the full screen. If you go to full screen, you see this.
Aspiration is you know some information on a black space, but clearly this island of white space.
Okay. So anyway, So Entanglement Islands are subregions in a gravitational universe. So whose information is fully encoded in a non-gravitational system that is in another universe. Yeah. So for example, in this case, just an intuitive demonstration of what's going on for the island. So you can have a soccer game inside the gravitational universe, like our universe. But then, so you can imagine that there's a monitor, like for example, in the haven, so where there's no gravity. And then, so you can instantaneously see what's going on in the soccer game, so in this non-gravitational region. So this is what is going on with the island. So,
what is a non-gravitational system?
I can give you a model momentarily.
You see a ball falling down, right, from the monitor. There's no gravity there, right?
No, I think you mean some dual theory that same information.
Yeah, that's right. So,
Why should this? Why should this?
So this system is subsystem of this. In ADS, it is easy to build this non-gravitational universe.
But this is just a mathematical description.
Yeah, this is just a mathematical description.
What's the definition of information? It's presumably, I think, you write a very, very long lines of ones and zeros, okay? But this line can have the length of 10 to the 100 or so or more, I mean, it's not limited. That's a certain information which the ordering of when you put unit, when you put zero, encode some information.
That's
right?
classical information. That's classical.
Okay, you have a long chain of spins. And some spins are spin up, some others are spin down. Is it okay? It's an information or not? It's a pure state.
Yeah. That's,
Okay,
yeah.
is it an information or not?
Well, okay. I would say I would say for me, the quantum way to describe information is really the operator. You give me an operator in a system, so whether I can reconstruct that operator so in another system or not.
Can you please explain? I give you very specific examples.
Yeah. Okay.
A chain of spins, heavy spins, okay?
Yes.
Each spin is attached to a certain atom, but it's spin one
Right. Give me a certain state.
collection of nuclei spin, but total spin is one half. And then I know that it can be spin up or spin down. So if spin up, you write plus, I mean, you number all them. If it is spin up, you write plus. If it is spin down, you write minus. It's a quantum system. Now you have, after you wrote it, spin up or spin down, it's in a pure state.
Yeah, that's right.
So what's wrong? What kind of operator I need? This is already an information which is ready for use.
It is information. It is a particular state in the system. It's a particular state in the proper space.
Particular state.
Yeah, that's right. I can start from a reference state and then try to go from that reference state to this state. So by acting on some operator on that reference state, then you reach this state. So everything can be rephrased in terms of operators. That is what I mean. Yeah, sure. You give me a state. Yeah, so it contains something. You can encode some information in that state. Yeah.
Okay, information is written in this state, but now I destroy this setup. You know, a big fire at the University of Minnesota.
Okay, you
totally destroyed.
You couple that with an
and you had no time to write up.
You couple it with an external system. The information goes to the external system. And the information is still there.
Where?
So that external system, the Minnesota. Yeah.
Can you extract back after you?
You can't extract it. It's like burning a book, right?
Burning a book, exactly. I'm always surprised when people say, okay, something written book, you throw it into the black hole and it disappears there forever. Oh, we lost
Well,
but
the question is to throw a phone book into the black hole.
Yes.
And are all the phone numbers encoded in the Hawking radiation?
Because that's what would happen if you burnt the phone book, right? If you burnt the phone book, there would be correlations, I think.
In the smoke and the ashes.
Exactly. But in the black hole,
it's different. Black hole has a horizon. You all see that. So
I know that black hole has a horizon. So your claim is that in the case of classical book, if I burn it, you say that all these ashes scattered in our Earth atmosphere can be somehow, by some mechanism, combined back and decoded.
You don't need a crazy mechanism. Unitarity in quantum mechanics just guarantees that. Just the Hamiltonian is very complicated. It's hard for you to simulate it with limited resources.
Hard or impossible?
Well, again, I think it depends on the resource. If you offer me another universe,
so how another universe allow you to collect all these atoms which are now scattered completely disorderly?
No, I mean, you use another universe to simulate what's going on in this universe, and then you have the access.
But there is no me who make the notes in another universe.
Well, I think I have in mind that the other universe, so there's some person doing experiment trying to encode what's going on in this universe and simulate what's going on. So I will imagine another universe is like a
there is no experiment. I just wrote. I just put spins in random order, spin ups and spin downs.
Yes.
It's an information, but I had no time to write it down and save it. Okay. And then it is destroyed by a huge fire. And in principle, some atoms which I used in order to put them up and down, they are in an atmosphere.
There's correlations. In principle, there are correlations that you could measure.
How could you measure?
Well, we don't. Imagine that you have a technology that you can now separate.
But they are now not in the same speed state. We lose the coherence. They were a coherent eigenstate. We completely lost coherence. It's impossible to keep it at large distances because only in the non-interacting world you can keep coherence once you created it. If there is even a small interaction, after some distance, it is lost.
No,
Weak interaction.
then you are saying that fundamentally we don't have quantum mechanics. Yes, then I have no way.
It's a philosophical question, but I think it's okay. I just don't, maybe, okay, I'll put it that way. Maybe in the audience, somebody understands the answer to this question. I made a coherent quantum state of many atoms.
Okay.
They were in a pure wave function. So lots of information, lots and lots. Now, due to the fire, the setup is ruined. And of course, coherence, because they are scattered all over, coherence is lost. How can you recover this information when coherence is lost?
Is coherence ever lost, or is it just extremely, extremely diluted, which could be
No,
compensated?
coherence is lost. If there is interaction, after enough time, the coherence will be lost.
Yeah. Then I think you are assuming so fundamentally have quantum mechanics. Yeah.
Why?
Yeah.
No, Misha assumes that there is some fundamentally classical systems that
no quantum mechanics.
Well, quantum, that's the
Well,
reason.
imagine that your
That's
process
the
of burning
reason.
is the interaction with other spin states, right? That you just scramble, right? And then the information hasn't disappeared but propagated to other parts of the wave function, right?
Okay,
If in practical terms, I agree with you.
no, it's
completely.
each time you lose a coherence, you lost 1/2 of the information. But here are two atoms.
You
lost
spread it
coherence.
in his language.
You-
You spread
you-
it over other wave functions.
So it's two, the probability you will be able to recover the original states is 2 to the power minus number of times interaction occurred during this process of fire. So it's law of big numbers, right? Any finite number of numbers, okay, in principle you can recover, right? If you know, but when this number tends to infinity, you lost.
Well, it's exponentially sensitive, I suppose. So,
Yeah.
okay, so it goes to zero, but it's not zero. I
Okay,
think that's the,
it's like you say in any finite system, quantum mechanical, there can be no phase transition. But we do observe phase transition because for practical, well, not even practical, I would say it, because it's the laws of large numbers. If the some number becomes exponentially small, that's okay. Then crossover, which is in principle smooth, but then it becomes non-smooth. It's a phase transition, and we observe it all the time. All our quantum physics is based, these are the most interesting points in quantum physics, on a phase transition actors. But in any finite system, it's not possible. No phase transition in finite degrees of freedom system, right? Then you say, okay, forget about, if I stand on your viewpoint, I say, forget about phase transition, because if you...
Yeah, I think that depends on the precision of your answer.
Exactly.
If you matter, if you are discussing questions, like in principle questions, then I can assume I can do measurement with infinite precision. But no precision, of course.
No, it's not possible in nature. In mathematics, it's possible. In nature, it's not possible. But I don't want to distract you from your topic.
Okay, but I think the question is well posed, so people think about it, and thanks for all. Okay, but maybe we should.
Okay, sounds good.
Thanks, Misha. Yeah.
Okay, I think the foundation. So what's going on here will be instantaneously known by that system. So you can see that. So this is something really acausal, non-local. There's something interesting going on, and we know that a very interesting example where entanglement island kicks into the physical process is the evaporating black hole. So
sorry, you mentioned the word acausal and something about the property of the first example.
This example. I'm saying that. So this is a property of the island. Yeah, by definition. So yeah, because by definition of island, is what's going on in the island will be instantaneously known. by this system which claims the island. So this is something A calls out non-local.
Okay, so let me say it differently. So you assume, so the red picture has its own dynamics, right? You assume there's a dual series that have exact same dynamics, encoded in a different way, but you can translate between them. So you just basically have a copy of the red.
What that's non-gravitational.
I understand. You change.
It's sort of duality.
It's a
one-way duality. I would say one-way duality. I would say this system is a subsystem of this. Yeah. If you think about it like a holographic duality, this system is a subsystem of that.
But is it possible if something happens, I'm failing in the black hole. I'm already beyond the horizon, but not yet assume, not something happens to me. Is it possible to simultaneously to project what's happening to me below the horizon on a screen in your lab? I don't think so.
I think it depends on the resource you offer. Same answer as before.
Could you please repeat?
It depends on the resource you offer me in my lab.
Resources.
Yes. Is it in principle possible because there is nothing which comes out from inside the horizon?
That's the classical picture. You assume locality. You have that conclusion. You assume locality.
Okay. Go ahead. Okay. Sorry.
Okay. Anyway. Interesting question. Very helpful. Yeah. So right. So to be concrete, so I'll consider a large black hole in ADS. For example, this part of the Penrose diagram. And then we know that large black hole in ADS is not evaporating, but I can make it evaporating by couple it with a non-gravitational bus, which is its half diameter. Yeah. So for example, there are some matter fields inside this black hole spacetime which obeys transparent boundary condition near the asymptotic boundary. So the modes of that field can freely leap into the bus. So in this way, you can trigger the evaporation for a big black hole in ADS. Okay. And then so the information paradox appears because you can imagine to firstly form this big black hole by throwing some photon sphere. So from the boundary, for example, start with photon sphere here, then you just perturb it a little bit and make it into the bulk a little bit. Then gravity kicks in, and then so that photon sphere will collapse. And then so that collapse will result in a black hole. And then so by Hawking's calculation, once the black hole is formed, so it will start evaporating. And then so you will have this Hawking process. For example, now I assume that black hole is formed, and then Hawking's calculation tells us that so there will be a bunch of this kind of EPR pairs continuously popping up over the time, also everywhere in the space-time. So here I just show you one pair for the sake of convenience of the discussion. So you have two partners of this EPR pair, and then one is inside the horizon, another one is outside the horizon. They are maximally entangled. So this one outside the horizon will enter into the bus. So for example, if you take a Cauchy slice like this, which is at the early time of the evaporation, then you will see that. So if you consider this part of this Cauchy slice in this bus, which is collecting this radiation, then by this calculation, the entropy of this bus system will be increasing over the time. And then that increasing entropy interpreted as the entanglement between this bus and the remnant black hole. So but if you indefinitely extrapolate this calculation, you will see that as the black hole evaporates, so that entropy will keep going. But then so at some point, so that growing entropy will violate Bekenstein Hawking entropy boundary. So you have this entanglement entity between the bus and the black hole. And then by Hawking's calculation, you will see that it is indefinitely growing if you extrapolate that calculation. Let's see, this is Hawking. And then, but if you look at the black hole entropy, you will know that the black hole is evaporating, so it is becoming smaller and smaller. So it's Bekenstein Hawking entropy is decreasing. So you'll see a different. So this is the entropy of the black hole. But you know that, so this entropy is the entanglement between the remnant black hole, or yeah, this is the remnant black hole entropy. So, but this entropy is the entanglement between the remnant black hole and the blast. So therefore, this entropy cannot be bigger than the entropy of the black hole.
I'm sorry, I'm confused about the terminology.
Okay.
The Hawking entropy formula, the one that's proportional to area. Which of these curves is it?
This purple curve.
So why are you calling the other one Hawking?
Oh, I would say this Hawking's radiation. Radiation.
Sorry,
Because that's
you're saying
Hawking
that's the
radiation.
entropy in the radiation.
Oh, that's the entropy of the radiation.
Of the radiation.
Of the radiation.
Okay,
You can have a variant of this where the second photon falls into another black hole, right? And then,
Yeah, that's right.
and then you're gonna have two entangled black holes. Is that the statement?
Between why do I?
Well, because the pair was.
Oh, you start with the two photon shells.
Right. One evaporates from one black hole and falls into another.
Oh, you're right. Yeah,
And then I mean, like path is not interesting stuff, right?
No,
Like
but it's very
it's already science fiction, right? Well, you just go into the extreme, right? Like
okay. I would say that the bus is under better control because in the bus you don't have the black hole formation. You can study the radiation by not studying another black hole.
Sure.
Yeah. But this problem is much easier than study another black hole directly.
so I have two, I think, very closely related questions. First, by the time that this intersection happens, can the radiation still be treated non-gravitationally? The more radiation you have, the more energy it has, the more mass it has, the more it potentially gravitates.
Yes.
And you're talking about, okay, so that's one question. The other question is, as the black hole radiates, it's getting smaller.
Right.
As it gets smaller, in principle, quantum effects should get bigger.
Exactly.
And Hawking's whole calculation is semi-classical. So do you believe any of this? Should you believe any of this, or is it all excluded instantly by saying that it's?
When the black hole is
Yeah.
large, you can't believe it.
My point is that by the time this intersection happens, it is not yet obvious from what was said that it is still large and that you can still believe this calculation. That's my question. Is it true that you can believe this by the time this intersection happens?
Well, I would say that you cannot believe Hawking's calculation at any instant during this process. But I'm just saying that
you cannot believe Hawking's calculation.
I mean, in fact. But you see the paradox by forgetting about.
No, but
yeah, I understand. And then your question is that at this point, is the black hole small or big, right?
I'm asking whether the quantum corrections are small or large at that point.
The quantum, yeah. So the quantum corrections are controlled by their parameters. Right? You have Newton's constant. For example, only in ADS, I also had LADS to be 1.
Yeah.
Yeah, so this is really dimensionless. And then so you also have this black hole entropy. The dimension is number. And then so you can have perturbative calculations in them. You can also have non-perturbative calculation corrections in them. Yeah, etc. Yeah, you have a bunch of quantum corrections. Yes. So the answer is that if you carefully incorporate that, you don't have this paradox at all. Yeah. You have this paradox here because exactly like you said, you just ignore the a priori. You see the paradox and then try to resolve this paradox by carefully incorporating this correction.
That's what I'm asking is, are you saying those corrections are important literally everywhere along the purple curve, or just if you go far enough on the purple curve?
Oh, along the purple curve.
Yes.
I'll say for the purple curve, you don't have to worry about this. The purple curve is very robust. The black hole entropy is literally A over 4 times G Newton. Well, you can consider
semi-classically, yes, but
no, quantum mechanically, that's also.
What does it mean, quantum mechanically? Come on, the calculation Hawking did is semi-classical. So why?
No. So you're asking for this curve, right?
Yes.
So this curve gives you an upper bound of the black hole Hilbert space, of the Hilbert space of the black hole. So this is an exact formula.
What does that mean?
So this gives you upper bound. So you should think of the black hole as a quantum. So you should think that there's a Hilbert space associated with the black hole, and then so there are many microstates for the black hole. So the number of microstates is given by the exponential of this formula. But this formula is exact. This formula only provides the upper bound.
You are saying that formula is exact in quantum gravity?
Yeah, this formula is exact in quantum gravity. That's true.
Why do you believe this?
No. Why do I believe this?
Yeah, why do you believe this? What reason do
We
you have to
don't
believe
even have quantum.
this? That's what I'm
gravity.
asking. That's what I'm asking.
That's
In
a
which
string
theory of quantum
theory.
gravity is
What
this
is
true?
quantum
What does it
gravity
assume?
at the scale of the Planck mass? Nobody knows.
States about that, yeah.
That is a holographic principle. Yeah, I think it depends on how serious you take the holographic principle. If I take the holographic principle seriously, so you know where this formula comes from, right? So,
Wait, look. The whole definition of area is classical. Come on.
no,
What do you mean by area? It doesn't make any sense in quantum gravity. Metric
So
fluctuates.
this is classical. This is
Yes.
classical. This is also in some sense classical. But this number is not classical. This number has a fine grained quantum mechanical meaning.
Yeah.
The number of
What
microstates.
calculation and what principle that you give?
Yeah,
Actually, this is the exact formula. That's the question.
yeah, the exact. Yeah, so I'm saying that.
Are you invoking like
The
Aaron
question
Ball?
is, this is exact formula if there are incorrections.
Oh yeah, then not
This
necessarily.
is
Then that will be corrected.
to begin with. This
Yeah,
is
that will be corrected. Yeah.
like okay, I could have quantum gravity corrections that are suppressed by I don't know 1/n² or something like that. We don't know.
Yeah, well, I mean, I'm saying that. So you can think of those as correcting the Newton. Yeah. But the fact that the number of microstates scales with well, given a subregion in the universe, number of microstates inside this subregion is upper bounded by the area of this boundary of the subregion. I think I will call that holographic.
I think I'm distracting you from what you want to explain to us. So please go on.
Okay,
It's okay.
Okay, anyway, yeah.
It's a good question.
Yeah, that's a good question. Yeah. Any question is it's helpful. Yeah. Oh yeah. So that's like I said. So this purple curve, you should think of this purple curve as providing an upper bound for this entanglement entry state. But then you can see that. So at some point, this purple curve will become smaller than this black curve. So therefore, we know that we cannot trust this black curve all the way. Okay. So the question is that what's going on at late time, for example, after this intersection time, right? So clearly, this picture is no longer quite valid. Okay. Okay. For that purpose, let me take a late time Cauchy size. Okay. I mean, late time is like after this intersection. For example, somewhere here. Then yeah. So then you should be able to say the decreasing. You should be able to say the decreasing of this of the actual answer for this quantity. If you're another color. Yeah, for example, you can speculate that so the actual answer might look like something like this, right? The exact shape doesn't matter; depends on the details of the problem. But then you should be able to see the decreasing. Yeah. So how come it decreases, right? So then the answer is that if you consider a late time Hawking pair, so this mode on the exterior should be entangled with this early time Hawking radiation mode. Yeah, so this is the physics after for example, intersection. Yeah, if they are entangled, then you will see the decrease. You will see the decreasing. So this mode enters into the box, right? Yeah, so that's the mechanism. But then the question comes because we know that by Hawking's calculation, so these two modes are actually maximally entangled, and we know that so there's monogamy of entanglement. So one spin cannot be maximally entangled with two different spins. Therefore, what's going on? So those two spins should actually be the same spin. Yeah, this is the proposal. So yeah, from here we can see that at late time, so this this interior Hawking partner is actually already encoded in this early time Hawking radiation. So yeah, so this is the situation for just like one pair or a few pairs of the Hawking radiation, early time radiation, late time radiation. But you can imagine this equality for many modes. For example, we have modes here, we have modes here, here. Then all these modes are encoded in like all the modes here. So that is how the island is formed. Yeah. So but that discussion, we say that so at the late time of the evaporation process, a large part of the black hole interior should be already encoded in early time Hawking radiation. So you can see that. So I take a Cauchy slice. I claim that the physics inside this red region is encoded in this blue region. Therefore, we know that this is sort of a large violation of locality or causality. Right? So if you just give me a quantum field theory, then this thing cannot happen. Yeah, so some intrinsic gravitational physics guarantees this to happen. then you will see the page curve. Yeah, you will see the so-called page curve. You will see, for example, we calculate this entanglement entropy of this of the bus, and then you should be able to see this increasing and decreasing page curve. The decreasing part is really because of the formation of the entanglement island.
Does this rely on the black hole in ADS, or this is for any black hole?
Oh, that's a subtle question. I would say that so this really relies on black hole in ADS coupled with a bus for subtle reasons. Yeah.
Oh, so this is not a description of a physical real black hole.
Depends on what do you mean by real black hole. Let's say in flat space.
On the center of our galaxy.
In flat, in flat space.
Yeah.
Well, I mean, I'll say that at the figure level, the answer for the SR in that case would be a constant.
I see. So this page code is specifically for this black hole in ADS.
Yeah, that's right. That's right. Yeah. Yeah. So there are subtle reasons. I don't want to go into that yet. Well, oh yeah, I should emphasize that. So it is important to get this answer that so this region is this system is not gravitational. Because this system is not gravitational, therefore it is under better control. You can just study this system directly, and then you can get this answer.
Right, and just check one more time. In which sense is that system non-gravitational? It has energy in it, and then
the equation is 0. Well, I just so this is ADS. This part is ADS, right? Asymptotic ADS.
Yeah.
So you have this asymptotic boundary.
Yeah.
Then you just impose transparent boundary condition, and then for a matter field, that matter field can leak into a bus. Bus is modeled, for example, by free scalar theory, if you like.
Okay.
Yeah.
Okay.
Okay.
We have like ADS space, and then like more space outside.
Yeah, that's right. Yeah, because there's an asymptotic boundary. You should think of ADS as a box, right?
Yeah, I know that. Yeah, but then
yeah. So you have something outside the box. Yeah.
Okay, in some sense, I actually view your black hole and the bus together as a quantum system.
Exactly.
That's a bigger system.
The bigger system.
You're assuming, the so-called information paradox is because I view the subsystem black hole. I seem to have some information loss, but the information is captured in my. It's already encoded in my blue region. So that I assume that's the solution you are going to propose.
Let's see. I think that's almost correct, but there's subtlety because at the end of the day, the black hole will be totally evaporated. Mm-hmm. So you end up with the whole system. You end up with
that's right. In the radiation, right? But you assume that there's entanglement and the information encoding.
Yeah, that's right. Exactly.
Very sparse the photon number and high photon number, but distributed space without the gravitational.
Oh, without the gravitational interaction. Yeah.
But the challenge is how do you show this works? This idea works. I have to.
Yeah, that's right. Yeah, that's right. I'll give a formula how to calculate this SR. Yeah. Any other questions? So some phases are a little bit confusing.
What's your statement about the maximum entanglement pair? I didn't hear that part.
Sure. I'm saying that if you go to late time, right? So you have this late time Hawking pair, this red pair. Mm-hmm. So they should be maximally entangled by Hawking's calculation. Yeah. But then we know that, so we expect the decreasing of this entropy of this green region, for example. For example, you evolve these Cauchy size a little bit into the future, such that this red mode enters into the bus. Then the bus entropy will decrease a little bit. So how to see how could this decreasing happen? So the claim is that this could happen because these two modes are actually entangled.
So it entangles with another?
Yeah, that's right. But for a good reason.
Okay.
And then so therefore, like this, I think you have in mind this monogamy of entangled, right? And then so that suggests that that suggests that somehow these two modes are actually the same. Yeah, because both of these and this are maximally, or like this is maximally entangled with that, so this is entangled with this, right? So therefore, in some sense, this mode is already encoded in the bus. Yeah. Well, I assume quantum mechanics all the way. Yeah. Comment question? Okay, sounds good. Okay, then we see that so the formation of the island offers us the solution of this information paradox. Okay, now the question comes. So for example, you could ask a simple question. So when could the island exist? And then also, what is the exact mechanism that the information inside the island is encoded in that reference system? For example, that path. So what is the mechanism? So what is the detailed mechanism, right? So some gravitational physics so should offer you that mechanism. So what is that mechanism? Okay, so a few comments. So the first comment is that firstly, so the two systems cannot be completely decoupled. If they are not interacting, so they just factorize from each other. So how come that one of the system is completely encoded in the other system? That's not possible. Okay, and then the second comment is that you will see during the talk that so a careful answer to this question will offer you the answer to the second question. And the picture I want to advertise is that so the actual mechanism that so the physics inside this island region is encoded in this non-gravitational system, which claims the island is that really they are connected by these microscopic quantum wormholes. Yeah, so they are actually connected by this quantum wormhole. They are macroscopic objects, and then they exist because of some gravitational effect.
So are they causally connected now?
But they're not causally connected. They're not causally connected. So yes, so these wormholes are really microscopic. But in certain cases, so they can be geometrized, and then so there is a mild violation of causality in those geometrized cases.
That's what. They are not causally connected.
In general, they are not. Yeah, because these are macroscopic.
That means that they are not connected. Period. Or
no,
there's no causal connection, then there is no connection.
No, I'm saying that. So those are macroscopic objects. You all see what they are.
Entanglement, so it's technical.
I'm saying that they are macroscopic objects. You shouldn't think of them from a large scale perspective.
So they're connected in the sense if like measure spin of one entanglement there, one universe, the other one like wave function collapses.
No, nothing that way. I'm saying that they are connected such that so that spin here is actually encoded already in this system. Well, but let me be more specific. You have an operator here, and then so you have another operator here. You calculate their commutator. The commutator is not zero because of this microscopic wormhole. You all see why. But that is the precise answer to your question. Yeah. Also, one more comment. So the origin of these microscopic wormholes are really the quantum entanglement. The quantum entanglement and gravity, they together offer you this microscopic object. And then so therefore, this is really an explicit realization of the ER equals to EPR conjecture.
So the number of these wormholes depends how many evaporation processes occurred, or this is some fixed links that I should be thinking.
You all see what these wormholes are momentarily. You all see what they are. They're actually not quite objects, but they are more like Wilson lines, if you like.
But normally in this duality, the non-gravitational theory is completely decoupled from the bulk, right? But here you're establishing some kind of connection between the two theories. Is that what you're?
Yeah. So I'm saying that. So I should think of this Karch-Randall. I think of this Karch-Randall. Sure. So there are some interaction Hamiltonian local here, but it doesn't matter. So if you consider quantum field theory, you take operator here, you take operator here, they should exactly commute.
No, but the black hole, the bulk there is dual to some 4D theory.
Oh yeah, that's right. So yeah, that's right.
Is that what your island is? Your island is this 4D theory. That's the non-gravitational physics. Or is the island something you've attached to a black hole?
Oh, the island is basically the interior of the black hole. The island is
this wedge, this wedge.
Yeah. So this wedge is non-gravitational. It's a box, non-gravitational.
But is it the dual description of the black hole ADS?
No. Right. So that's a good point. I will say that naively. Well, let's see. You can first remove the box, right? You just look at this asymptotic boundary. Right? So yeah, standard ADS-CFT tells you that. So all the physics inside the ADS is encoded in this one-dimensional lower subsystem. Yeah. But then I'm claiming that now you attach it to a bus. So the way holography works is different.
Yes,
So now,
you're modifying the usual story, right?
That's right.
It's path to the boundary.
Yeah, that's right. That's right. Yeah. Then you will see that the big part of the ADS block is actually not encoded on its boundary, but encoded in this external reference system. Yeah.
Excuse me, that's my last question.
No, it cannot be.
May I deviate a little bit from black holes?
Okay.
Do you think you can, or somebody else can prepare a pure state of you, of any person in this audience? Pure quantum mechanical state. Pure, not, I mean, I know we are all described classically, but if some person with unlimited, as you say, resources decides to make out of you a pure quantum mechanical state, do you think it's possible?
That's possible. Well, let's see. I assume that I have a non-zero overlap with my ground state. Now, if you isolate me from this everything.
No, not if. You cannot isolate. Nobody can isolate nobody else from nature.
Okay.
We exist in certain conditions. Okay.
Okay, then I can.
We exist in certain conditions. I agree with you. There may be somebody or something which has lots and lots of resources.
Okay.
But how do you think is it possible to isolate you?
Okay.
Before doing something, because you will be evaporated. I mean, if you put you in the vacuum chamber, it's very good. Yeah, eventually you will, I mean, spend, if the vacuum is very good.
Do I have a free Hamiltonian? Yeah, if you give me that free Hamiltonian, assume that I have non-zero overlap with the ground state of that Hamiltonian. You just evolve me using that Hamiltonian.
Okay, yes and no question. Do you think it's possible to prepare a pure quantum mechanical state from such a macroscopic object that's, let's say, a human being, a force, or I don't know, whatever?
Okay.
Is it possible? Even in abstractly speaking of someone who has unlimited resources. I cannot think. Basically, you are speaking of God. Who have unlimited resources?
Okay, then if there's no unlimited resources, then that's not. Okay. The answer depends on what you offer.
So, okay, I think that's the answer, which I wanted to extract for myself. Thank you very much.
Okay. Actually, what is that answer? Could you please summarize?
But you needed unlimited resources.
But you need God to make progress.
For this question?
I think that's what Misha suggested.
Oh, okay.
Because in nature, there is nothing which has unlimited resources, right? It cannot be.
No, I think
by definition, if there is something which has access to unlimited resources, that's God. I can call it God. You can call it whatever, but you don't even want to do that.
Look, I think there's a subtle difference. This question already appears if you assume you have unlimited resources.
Yeah. I don't assume that because that's not possible.
Okay, then there's no question to start with.
So you would say that yes, let's imagine there is God with unlimited resources, but God still plays by some rules, right? This is like
that's a different story. About God, it's a totally different story. We can go into that, but we won't be able to solve that. But when people say that you have to have unlimited resources, in particular, you have to have unlimited amount of nucleons, for instance. But in the causally connected universe, we have only 10 to the 8 nuclei.
Right.
So it's limited by definition.
Right. So
it's limited by definition.
Yeah, then that system is by definition not a unitary quantum system.
Okay. So why do we discuss highly hypothetical situation where there is something which has unlimited resources?
Yeah, so the reason that we want to understand how gravity works quantum mechanically, that's why we want to formulate an exotic question. to test how gravity works on the
I agree with you.
Lisa, yeah,
If we
yeah,
can-
this is all in ADS on top of
Yeah, that's also good.
Well, you may say that IDS world, I mean, there is something which has unlimited, I don't even know how to formulate unlimited resources. Nothing is unlimited in the area which is causally connected with us.
This is, I agree with Michelle, this is very unpractical and very kind of philosophical, conceptual.
Philosophical, then it's a religion. And then everybody is entitled to his or her own religion.
Let's see if he has a mass.
There are some rules
Continue to.
Let's see if he has mass. Some calculable.
Yeah, that is good. I think you should keep asking my question.
I said that's my last question, so you can go on.
Okay, sounds good. And the last comment is that these two problems actually reflect some these two problems reflect some deep connection with subregions and locality in quantum gravity. I think these things are more or less what we are talking about. So in QFT we know that we can define subregion, and then we can define observables localized in the subregion, and then also because we have the notion of locality. But based on that previous discussion, we know that that notion should break down in quantum gravity. Okay, sounds good. So here's the okay, by the way, I think I heard from Tony I'm going to go over. So yeah, I don't think I have unlimited resource to give this presentation.
You'll have to speed up.
I'll have to speed up. Oh, okay. Okay.
This beats the record of the hierarchy problem. Actually, that's true.
Do I have 1 hour?
You've probably beat the record for
Outline.
the outline. The previous record was 30 minutes. Might have been 45 or 45, but you've gone to 50, so that's
50.
You have the record.
Okay. So I'll first see a few bits more about the island model. So I'll give the formula. I'll try to convey the message that what I said previously are not simply words. So I will convert it as a calculation exercise. Okay. And then I'll explain an important property of the island model. That thing that the gravitational part of the island model is actually the Higgs space. And then I'll try to consider the consistency of the island in the island model, so to impose some consistency conditions. And then then we'll see that the solution of those consistency conditions offers us the mechanism for that previous question. And then I'll give you a toy model to visualize this method. And then I'll end up with the implication and summary of this talk, if I have enough time.
Realistically, you have like 10 minutes. So.
Well, I have 10 minutes. Okay, that's okay, sounds good. More on the island model. Okay, the island. I define the island model like you have an asymptotic anti-de Sitter universe, for example, d plus 1 dimension. So there are some unknown things. So anything can happen in the bulk, but to ensure that the asymptotic region is ADS. And then you couple this asymptotic anti-de Sitter space to a non-gravitational bus of the same dimension. So this is my definition of the island model. So this model is the gravitational region coupled with a gravitational system coupled with a non-gravitational system. And then in this system, you can use this so-called quantum extremal surface formula to look for entanglement island. So how does this work? You take a Cauchy slice through this whole system, and then you specify a subregion in this non-gravitational external system. So we look for the von Neumann entropy of this subregion. So this is well defined because this system is non-gravitational. The subregion can be defined. Subregion observables are also well defined. So the formula for this quantity is really this. So you have to look for this so-called island region inside this gravitational part. And then you take the area of the boundary of this island part, you divide it by 4 times G Newton. And then you add that with the matter entanglement entropy for the matter field inside this subregion R and this gravitational subregion I. And you have to minimize over this I. So the output of this formula is the entanglement island. And then the boundary of the entanglement island is a so-called quantum extremal surface. Okay. Okay, and then to study the physics of island, so I can of course study evaporating black holes we discussed, but the geometry is a little bit complicated. So therefore, I won't directly study this. It's slightly more simplified system is you study the eternal black hole in ADS, and then couple it with two external bars with the same temperature, this eternal black hole. Therefore, there's no evaporation. So the geometry is still static. And then in this system, we can take a Latam Cauchy slide like that, and then you specify a subsystem R, which consists of two parts R1, R2. Use this formula to look for the von Neumann entropy of this subsystem, then there would be entanglement island, which overlaps the interior of the black hole. But this system can be studied, but the geometry is still a little bit complicated. Therefore, I want to further simplify the geometry. And then we can go to the empty ADS. We can consider an empty ADS universe. You couple that with an external bus. You can do this, and then you can do pretty much the same. You take a Cauchy slide, go through the empty ADS in the bus. You specify subregion on the bus, and you use this formula to look for the entanglement island. So you'll see that. So if this subregion R is large enough, and then you will have a non-empty entanglement island inside this ADS, this empty ADS. So this is the setup I will talk about in the rest of the talk. Okay, very good. Okay, for that purpose, we can go to the dual description. So the dual description is really, we start with an empty ADS D+1. We couple it with a D+1 dimensional bus. So we can dualize that system to a D-dimensional CFT living on the boundary of this bus. So this is a dual description. So in this dual description, so I have two subsystems to start with. I have this CFT D, which has an action, so which I don't specify. Also, I have this bus, which also has an action. But then these two systems are coupled with each other. For example, here I deliberately take this double trace deformation, which couples them together. And then this double trace deformation is marginal. Then we have this O1, O2, they are single trace operators. So O1 is an operator, so on this CFT D. O2 is an operator on this D+1 dimensional bus system, but you extrapolate that operator all the way to the boundary. So you just multiply them together to couple these two systems. This is a dual description. So corresponds to the ADS case that this double trace deformation corresponds to you have a leaky scalar field inside the ADS. For example, you can study you can have a free massive scalar field phi 1 inside the ADS. Then you impose a non-reflective boundary condition, or you impose transparent boundary condition. Means that so the near asymptotic boundary behavior of this bulk field is like this. You have both z to the power of delta, which is called the standard quantization, and the z to the power of d minus delta, which is called the alternative quantization. You have them independently. So this is the leaky boundary condition. And then, so for example, you can calculate the green function from this quantization condition. You will see that the green function, the two-point function of this leaky scalar field, is a linear combination of the green function for the standard quantization and alternative quantization. Of course, with this coefficient controlled by the coupling strength. So this G and this G, they're really the same.
I have two questions. One is, can I get a sense of geometry of size, right? You have this quantum extremal surface. Suppose there's some scale associated with that.
You're right.
But how large in my reference system needed? You always say, from particular radiation, you need the subregion reference system to correlate the information.
Right, that's right. So
for a whole black hole object, do I need infinite size of the reference system to encode all the information? Or
you don't need. So you just need a yeah. So for in this case, right, you can take this R to be a subregion. So then you look for the island.
Yeah, for a particular line, a particular radiation, let's say that information is encoded.
Yeah, that's right.
If I view the black hole as a whole, including all its radiation, do I need infinite space to encode that? My reference system.
I think you're saying that. So we can use a bus which is not infinite. Yeah, you can do that. Yeah, you can consider bus to be another bus. You can similarly use this form.
Okay. Second question. Go to the next slide. Can I go next slide?
Sure.
It seems to me the black hole doesn't play any special roles here. I can say, oh, I have a quantum system, right?
Exactly.
Exactly same formula.
Exactly.
Just talking about quantum mechanics, assume the properties between how they interact with the
yeah, that's right. But you need you need gravity in this ADS part. Yeah. That's all you need. That's all you need. Yeah. So the existence of the island is really a property of the quantum state. Yeah. So that means that, so well, for example, from this formula, you can see that. So how could you have an island by minimizing this, right? So you just have to make sure that this R and I, so the entanglement between R and I is big enough. And then therefore now, so you give I to R, then so that entanglement is significantly reduced. Yeah, so that is property of a quantum state. Of a particular feature of the quantum state, so not a specific quantum. I mean, the feature is entangled. Okay, sounds good. Yeah, we have this green function, which is a superposition of the standard quantization, alternative quantization. Okay, sounds good. Now, I want to explain to you that, so this island model has a very interesting feature that, so this ADS part is actually in the Higgs space. So how to say that? Yeah, so I'll do the linearized analysis to the leading non-trivial order in G Newton, but this lesson should persist to any order in G Newton, but I will focus on the leading order in this discussion. Okay, so I linearize this bulk metric. So in this way, you have this background metric, so which is empty ADS. So you have this this fluctuating part, so which is like a perturbative graviton around this empty ADS geometry. So the partition function of the ADS part, or the perturbative partition function of the ADS part, can be written like this. You have the path integral over this graviton field. You have this leaky sphere field. Sorry, this should be phi 1 instead of phi. And then you have their interactions, right? And then if you look at this path integral, then you can perform a D-field transform. To leading order, the D-field transform doesn't transform the matter. I mean, to leading order in G Newton, it only transforms this graviton field. And then you will see that because of that leaky boundary condition, so this system is actually not invariant under the D-field transform, or under all the D-field transform. You can see that so by plugging everything, and then so by plugging all these results into this system, you'll see that so there's a large boundary contribution because of the lead phase. So what's the physical meaning of that? So this is a signature of spontaneous symmetry breaking. So this type of behavior that the bulk global symmetry is violated by boundary flux term is really a signature of spontaneous symmetry breaking. Okay. So from there, so we can try to decode the Higgs physics. For example, I want to say that the graviton has a mass. And then I want to say that there's a vector goes to boson associated with the D-field broken. Right. So that's the goal for the next discussion. So how to say that a vector goes to boson? So I start with this action. There's no vector goes to boson. And also it is not so clear how to construct the vector goes to boson from this matter field. So but there's a very interesting trick that we can introduce this auxiliary vector field, and then so we couple this auxiliary vector field so with the matter's rationality tensor like this. But then we don't give this field any dynamics, and then we just ask this field to transform under D field together with the graviton this particular form. In this way, we restore D field invariance. So the trick is that you first introduce something auxiliary to restore D field invariance. But there's no independent dynamics you offer to this auxiliary thing. And then so you can study the quantum correction from the matter field to this auxiliary degree of freedom introduced and the graviton.
Is this one trick?
Sort of, yeah. Yeah, that's right. So I will say that Stuckberg is the subclass of this trick. Yeah.
I'm sorry, what is the second action after the Einstein-Hawking action? Yeah, that one.
Oh, Einstein-Hilbert.
Oh, Einstein-Hilbert even, sorry, but after that, which is...
matter.
Oh, okay,
yeah,
sorry.
Phi 1, Phi 1, not Phi. Sorry, yes, but this should be bigger. Okay, sounds good. So we have this manifestly D-field invariant path integral. And then so the goal is to study the quantum correction from the matter to the graviton and the vector system. And then we know that, so for example, we can imagine to integrate all of the matter in a good sense. And it's to say what kind of effective action will be generated at the IR. And we know that that effective action should be d field invariant because we start with something manifestly d field invariant, so I should end up with something which is also d field invariant. And then therefore, so that effective action should only depend on this d field invariant combination between this V and the H. So that d field invariant combination is literally this part. Yeah, so therefore, to simplify the calculation a little bit, so I can firstly set the graviton to be 0. I just focus on the vector, and then I get a vector effective action, and then at the end of the day, I replace a vector by that d field invariant combination. So let's do that. Now, firstly, set the graviton part to be 0. So I want to calculate the one loop correction from the matter to this auxiliary vector. So this is the effective, this is quadratic effective action. And then this is non-local. You can see that. So there are two integrals, basically two vertices in that one loop diagram in the real space. Yeah, so this is the Feynman diagram. Right, and I want to isolate low energy part. So therefore, I should take the large distance limit between these two vertices, x here and y here. I take the large distance limit for this matter stress tensor two-point function. So the result is that, so this matter stress energy tensor two-point function is in this particular form in the large distance limit. And then this D satisfies this sort of Green function. And then we can use this result. We can plug this result back to here. And then so we do some integration by part. For example, to move one of the derivative into that part. And then so you can see we'll have another differential operator at x acting on this D. And then we can use this Green's function. In this Green function, I will have a delta function. That delta function will kill one of the integrals. And then so we will get a local effective action at the low energy. So the result is this. So that coefficient in the form is parameterized as mass, as m squared. So yeah, just parameterize it as m squared. M squared scales with the G Newton and the LADS in a particular way.
So is that the different variant order parameter?
Oh, the V. Oh, the V is a Goldstone field.
I don't know. What is your diffeomorphism invariant order parameter?
Orders. Oh, that's a good question. I haven't. Oh, did.
But you have spontaneous symmetry.
Yeah, that's right. So
that have a diffeomorphism invariant order parameter. What's the origin of that?
Yeah, so that part is not yet understood. But I'll make a comment on that. Yeah. So this V can be studied holographically. That's the best I can offer at this point. Yeah. I will say that the order parameter is not different here. Yeah.
No, the order parameter should be diffeomorphic.
Well, I mean, the U1 case it should be. In the U1 case, you have 5 star 5. If you call that order parameter, it's
that's the order parameter. It's gauge parameter.
Oh, but I'll call order parameter 5.
Yeah, but that's not different variant.
Yeah, that's right. That's right. I'm not sure if there's a different variant order parameter.
In this theory, you're saying
in this theory,
you haven't identified it.
I haven't identified it. Yeah.
There could be a gauge artifact then if you don't identify it.
Gauge artifact.
Of the diffeomorphism and variants.
I don't understand that. Could you please explain it?
I mean, if the field that's getting a VEV
yes
is gauge dependent, then
yes,
then I can do a gauge transformation to get rid of it, right? So you have to tell me what is the diffeomorphism.
No, I'll say the gauge transformation is the Goldstone boson for that gauge non-invariant order parameter. So, but I haven't identified that. I don't know what it is yet. Yeah, sounds good. And so, like I said, we can restore this graviton, get this invariant combination, and then yeah. So from here we got this action. We got this quantum generated effective action. So which is exactly the Fierce poly, the covariantized Fierce polymass for graviton. Okay, good news. Okay, sounds good. So now I hope I convinced you that the gravitational part in the island model is in the Higgs field. And then the D field or the global part of D field is spontaneously broken. The graviton is massive. We have additional boson vector mode. Okay, so now I want to impose some consistency condition for the island. So the first consistency condition is really the gravitational Gauss law. So what is gravitational Gauss law? So classically, it is a simple statement that if you have some massive object sitting somewhere in the gravitational universe, you can extract the value of the mass by measuring the gravitational potential on the sphere which contains this matter source. Yeah, so you can see that classically there's already something non-causal, non-local in gravitational system. Okay, and then quantum mechanically, the gravitational Gauss law can be formulated using this ADM formalism. So I start with parameterizing the space-time using this ADM parameterization, and then I have this lapse function n. I have this metric on the spatial slice Gij, and then I have this shift vector Ni. And then you plug this parameterization back to the Einstein's equation. And then so there's an interesting thing that appears, which you will see that, so there's actually no time derivative of the n and Ni, so in this action. So therefore, this tells you that the canonical momenta associated with this lapse function and shift vector, they should be zero. Right? So this is called the primary constraint. And then we know that so this constraint should persist over time evolution. So that generates the secondary constraint. The secondary constraint are really this Hamiltonian constraint, the momentum constraint. Yeah, so it tells you that the total Hamiltonian of the gravitational system is zero, and the total momentum is zero, which is not surprising. We know that there's diffusion morphism invariance as a gauge symmetry. So therefore, the associated charges should all be zero. Okay, so now I want to analyze this Hamiltonian constraint. I'll analyze it to the linear order. I linearize this graviton field. So the zeroth order is this result. So you can plug in the empty ADS to this result. You will see that this is zero, so which is not surprising. You start with a good background. The background is unshell. So therefore, there's no linear instability. And then you study this linear level Hamiltonian constraint. And then you got this result. So you have this graviton part, the matter part. This H is a matter Hamiltonian density. And also you have the graviton Hamiltonian density if you go to 1 order higher. So from here, you can see that I haven't taken into account of the graviton map. I should say that. So and then you can start from here. And then you do the integral over the Cauchy side. And then you convert this Hamiltonian density to a Hamiltonian operator. And then this part will also be integrated. And then do that integral, you will see that. So that integral is actually the same as the boundary term. So this tells you that the matter Hamiltonian in the gravitational system should be equal to a boundary term. That boundary term, for example, given on the asymptotic boundary of the ADS, the boundary term is linear in the graviton. So this is gravitational Gauss law, which is not, which is more or less a quantum version of the classical Gauss law. Right? You have some matter source in the bulk, you can marry that on the boundary on the same Cauchy side. Okay, this is the constraint we want to impose for the operators inside the ADS. So let's say I take an operator OX inside the ADS, so that operator should obey this diffuse constraint. So this tells us that the commutator between this operator and the boundary Hamiltonian is actually a time derivative of this operator. So therefore, this is already a signature of non-causality, non-locality, if you take into account the quantum effect of gravity. But then we can see that here's the trouble with the island. So because let's see, I should say here is an island part. Here's an island. So this operator O is inside the island. And then so as we said before, this operator O is really encoded in this external system. In this, for example, the O should be equivalent to some operator, which lives on this non-gravitational bus. I call that operator OR. So that operator can be smeared a little bit, which is not necessarily like a point-supported operator, but it is an operator in that system which claims the island. But however, we know that in that non-gravitational system, so there should be locality and causality. So therefore, this blue blob operator should commute with this boundary operator on this non-gravitational system. So therefore, this suggests that this H boundary and OR should commute, and OR is the same as O. So therefore, H boundary and O they should also commute. But that is not consistent with this, right? We just see that they do not commute as a result of this constraint. So what's going on? How to resolve this contradiction? So the answer is very simple. So we have to take into account the graviton max term. If you add that back, you will see that so there's this additional term on the Hamiltonian constraint. And physically, you should think of this as this graviton mass gives a utility of the gravitational potential. Therefore, you're no longer able to detect some matter source inside the box from the boundary because you no longer have the parallel decay. You have the exponential decay. Yeah. But algebraically, it is seen that the constraint is modified by this additional term. Yeah, so if you study the integrated constraint as before, then you will see that, so this is the new constraint. So to the leading order in G Newton, you can ignore the graviton kinetic, the graviton Hamiltonian. Then you can see that you have the matter Hamiltonian, you have this boundary Hamiltonian, which is also called ADM Hamiltonian. So you have this additional term from the graviton mass. And then this additional term is exactly canonical momentum of the zeroth component of this Goldstone vector field. And then so from here, you can see that you can solve that constraint. You impose this constraint to that matter to the operator inside the island as before. You can see that so this solution of the constraint satisfies this is solution of the constraint, and also this commute with the boundary ADM Hamiltonian.
So in human words, you're trying to show the because this partial H commutes with both sides of the operator, you show it's possible to define an island that is around the black hole that information is isolated, and then to couple it the information O black hole to OR in the reference system, saying information is coupled there.
Yeah, that's right.
It's non-causal connection. It's just that you demand the system have such a
Well, this is a consistency condition.
Yeah.
The island should obey. The operator in the island should obey.
So you're showing it's possible to define an island then due to this.
Yeah, that's right.
But only if the graviton has.
It's massive. It's massive. Yeah.
In this setup, it's consistent.
In this setup, it's consistent. Yeah. You can extrapolate this to see that not in this setup, so there cannot be island. Yeah. That's a strong version to do the extrapolation. Okay, sounds good. Then we can see that so this operator obeys the constraint. So essentially, so we know that so the commutator between H matter and this thing is non-zero, but that non-zero is cancelled by this commutator between the between this pi and the v. So that's why we can still obey the constraint, but this operator commutes with the boundary Hamiltonian. Okay. So we can see that so the graviton mass resolves an important issue for island. And also we know that so there's another consistency condition because as we said before that so this operator inside the island is secretly some operator in the bus. So any operator in the bus should accept bus Hamiltonian, right? So because the bus is a non-gravitational system, so any non-trivial operator will accept bus Hamiltonian. So the question is that so how could the operator inside the island have a non-zero commutator with the bus Hamiltonian? So that's the second consistency condition we want to study. So we should have this consistency condition. So the answer is, how is this possible? Also, we know exactly what is this O physical, right? And then so this O part is really some bulk operator when there's no gravity. And this V is like some bulk effective field, which also lives in the ADM. So how come this thing has non-zero commutator with H Hamiltonian? Oh, sorry, with H bus. So the speculation is that so this V part secretly has a non-zero commutator with H bus. So that's the speculation. So the question is that how is that possible, or how to show that, how to prove that? Okay, and then to answer that, Tony's question kicks in. So a few comments. So we know that so the V is a Goldstone vector associated with the spontaneous breaking of the D field, and also therefore, if we are able to identify an order parameter, so let's say for me, the order parameter is not necessarily gauge invariant, and then I do a gauge transformation of that order parameter, I'm able to get the Goldstone ball. That's my goal. But even that is not straightforward. But we can already motivate an answer a little bit by the following observation. So we know that so the D field in the ADS is spontaneously broken really because of the bus, right? If you don't have the bus, you don't expect the D field to be spontaneously broken. So the reason that diffuse broken is really because of the entanglement between the AD and the bus. So therefore, a natural order parameter, a natural non-gauging invariant order parameter, you can imagine is that it's a bilocal operator. So we have this phi1 living in the ADS, and you have another operator, so inside the bus. And then because of that entanglement, because of the leakiness, you have a non-zero correlator, and then this non-zero correlator depends on this location of the ADS field. So therefore, operators like this are good order parameters. But the issue of this simple order parameter is that there are many order parameters like that. So for example, we can need y to be anywhere in the bus. You can also smear this phi to y a little bit. So they are both order parameters. So which one is a good one we should use? So that is not so clear. I don't know the answer for that. But if we roughly take this to be the order parameter, and then we can see that so this v is roughly like in this form, right? So you start with this order parameter, you perform a gauge transformation to order parameter. So this transformation of the order parameter is v. And also we can see that so this operator has a part supported in the bus. So therefore, it is not hard to imagine that. So this v has a non-zero commutator with bus from this perspective. Yeah, but exactly what is the value of this commutator? So we can deduce this using a little bit of holography. So a few quick remarks. So we know that so the graviton in the ADS is dual to this CFTD stress energy tensor. And then so this V is like the transverse mode of the graviton. So it should be dual to the divergence of the CFT stress energy tensor. And then that divergence is non-zero because of this double trace deformation. Right, so you can calculate the divergence of this CFT stress energy tensor due to this additional coupling term. We got this result. So really, V is holographically dual to this composite operator. Yeah, then we can try to understand the transformation property of V under the bus translation, understanding the transformation property of this operator. So under the bus translations. I call operator U for convenience. And V and U should be related by this extrapolate dictionary by ADS-CFT correspondence. So you start from, by the way, you should imagine you restore this ADS-B plus 1. You start from the field V, and then you move that very close to the asymptotic boundary. So it scales immediately with this U operator and the small g. Okay. Now you can do some calculations to try to understand the transformation properties of this operator U. For example, you can firstly do a CFT translation. So U transforms in this simple way. So you have this O1 part, right? So you just do say CFT translation. The O1 part will have some partial mu O1, and then so you have this CFT translational parameter. So this is how the U will transform. But the interesting thing that so the O1 O2 2-point function is not zero due to this double trace deformation. So therefore, what you should really do is that so this O1 O2 is not a good operator. You should subtract and add its maximum expectation value. You should subtract its maximum expectation value to get a good operator. So therefore, from here we subtract and add that maximum expectation value here, and then we get this result. And then the goal is to calculate this because we know that this is good operator. It has zero value. This is good operator. It has zero value. So we have to calculate this. So this can easily be calculated to leading order in G using conformal perturbation theory. Yeah, so the result is simple and it is divergent, which is not hard to imagine. Because I'm doing a marginal deformation to the CFT plus bus system, there's no scale introduced. So therefore, this O1, O2 has a non-zero conformal dimension. So therefore, this 2-point function can only be dependent on a small UV cutoff, so which I call epsilon. And it is in this particular form. So from here, we can see that so to order in this small epsilon, we know that the U transforms like this, right? The simple shift by this divergent T. And similarly, you can see how U transforms under the bus translation. So by almost the same calculation, so you get this result. Also shift by constant, so which is divergent. So these two epsilons are the same short distance cutoff from the field theory. And also we know that so from holography, So the CFT translation is really a bulk translation, right? So therefore, if you do a CFT translation, it is like you perform some isometry transformation for this V. The V is Goldstone boson, therefore V is shifted by a constant. So from that, you can see that so this epsilon and this short distance bulk cutoff should be the same. You should identify them. And then this C to the power of 2 will cancel this epsilon to the power of 2. Then you can see that so the V mu transforms like a Goldstone, literally Goldstone boson under the CFT translation symmetry, which is due to the bulk isometry, which is the global part of the D field. And then from there, you can see something interesting because this U actually because this V actually transforms under this Bass translation. Because you do a Bass translation, so it translates U like this. And then because of that previous argument, we know that we have to identify this epsilon with the Z, which is short distance cutoff. You just plug this in, you'll see that V also transforms by constant shift under the Bass translation. So this offers you the answer to that previous question. So yeah, you can see that. So the commutator between H Bass and this V field is actually big, which is not zero. And also, this is a constant. And then from there, you can check the commutator between this stress operator, in the island and the Bass Hamiltonian. You can see that it's simple time derivative with a constant coefficient. So this is the answer to that previous question. What is the reason that so the operators in the island can excite the Bass? And also, you can extrapolate this a little bit, seeing that so the mechanism, the information inside the island is encoded in the Bass is really because of this V dressing. You should think of this V as these quantum wormholes. So these quantum wormholes are really the V field. And we know that so V is from the quantum entanglement between the ADS and Bass. That is the origin of the spontaneous symmetry break. So therefore, this is really a manifest realization of the ER equals to EPR proposal. Okay.
Probably, yeah, you could probably get to the summary because some people have to leave it too.
Oh, okay, sounds good. Okay, then I'll skip this toy model part. Maybe a few quick comments. I think okay.
If you have a few quick comments.
Okay, a few quick comments is that so there's this particular model of the island model, like this is a holographic model. So in this case, you can easily visualize about this quantum wormhole. So the idea is that so when the entanglement between the gravitational part and the non-gravitational part is extremely large, then this quantum wormholes will condense. Then this quantum wormholes, this condensation of the quantum wormhole is some geometrized object. You will see some emergence of the extra dimension connecting them. So yeah, so that model is called the Karch-Randall braneworld. In that model, so we have this ADS-D+1 living on this brane, and then in the bulk we have this ADS-D+2, and then this is the emergent extra dimension that is connecting them. And then that V field, is actually this extra dimensional gravitational Wilson line. A more precisely, KK component of this extra dimensional gravitational Wilson line. Okay, let me maybe wrap up the talk with the implication summary. So firstly, we uncovered the mechanism behind the information coding for entanglement island. So this mechanism is really a combination of gravity and the entanglement. We need the entanglement to spontaneously break the diffeomorphism, and then we need gravity to impose gravitational constraint and solve it to have this explicit stress operator that it has a non-zero commutator with a Bass Hamiltonian. Okay, and also we see that the island is an explicit realization of the ER equals to EPR. And also we see that the graviton mass is essential for this story. And also a bonus is that, so we can draw some papers saying that if you consider a closed universe, then you study quantum gravity on the closed universe. So naively you might think that so there's no non-trivial observables inside the closed universe if you take gravity into account, because it is like you consider gauge theory on the sphere, there cannot be any charge. So there's a gravitational version. So this. So Witten said that you can add an observer Hamiltonian. So that observer Hamiltonian is of a particular form. So it's linear in the phase space variable. So Witten's observer is that you add this observer Hamiltonian, which is H equals to Q. Q is like the position of the observer. And then so at this observer Hamiltonian, you can drag observables now to this observer, such that so you can have non-trivial observables inside the gravitational universe. And then so we can see that, so in our case, that correction from the graviton mass to the Hamiltonian constraint is literally linear in phase space variable. So this is an explicit realization of Wheaton's observer. Okay, that's all. Thank you very much.
Had a lot of discussion. Are there any more urgent questions for our speaker?
How to build a wormhole?
Well, how to build a wormhole?
Wormhole, how do you build it? How to build, create a wormhole?
We try to entangle them.
We
try to entangle them first. So how to entangle them? We couple them at some point, and then you decouple them in the future.